Hello and welcome back to Calculus 1, section 4.3 on the first and second derivative test. The textbook does have the ridiculous title of what derivatives tell us, like they can talk, right? Maybe if they said show or something, whatever. It's just weird. So we are going to observe a function today, the graph, and realize what it means to have increase and decrease, even though we talked about it. I believe it was all the way back in chapter 3, 3.2 or something like that. We talked about the derivative being negative or positive and all of that stuff. All of that is back now. So if I draw any kind of a function, I can break that function at these mean and max values, which are the critical points. And also, I can break this function at something that we haven't talked about yet, which is called inflection point. And then there is also another part of that, another situation where you can break it apart, which was, if you remember, the vertical asymptote. But let's leave the vertical asymptote out for now. So when you have some kind of a maximum, we don't care which one, right, local or global, we have a max. The function has to be increasing into max. So this is where the function is increasing. And then also getting out of the minimum is also going to be increasing part. So there are, in this case, now two locations at which we have the increase. We also have this situation in between, right here, where we have a decreasing function. So that's a decreasing part. And that one is, again, getting out of max. Since it's a maximum, you can only go down. And then, obviously, that would lead into a minimum. And once you reach the minimum, you are at the lowest point. So you decreased, right, into the lowest point. And then from the lowest point, you can just increase and go back up. So it's very easy to conceptualize all of this when you look at the graph from left to right. You can also imagine yourself walking on this line. So you're going uphill, that's increasing. Going downhill is decreasing. And we're going to find a way to compute those things now without actually having the graph, because we're going to use those ideas to graph functions later in the next section. So that's going to be next class, to graph functions without the calculator. So now let's talk about first derivative test. Oh, also I did not mention yet, but maybe I could add to this graph as well. If I break this inflection point here, I hope you see that to the left of it, let's use what color? Yellow, I guess. If you take a look at this part here, you see that that is like the cup that opens downwards. And we will call that concave down. Let's use the rainbow over here. Concave down. And on the other side of this point would be a cup which opens up. How about this ridiculous blue. And this would be concave up. So one spills the water, one holds the water, right? The cup which opens up, right, will hold the water. And the yellow one, which opens down, is like when you put the glass upside down, it will spill the water that is inside the glass. And those are the two concepts that we are after today. Increase, decrease in the first derivative test, and concavity, concave up, concave down in the second derivative test, which is enough for us to, in most cases, analyze any function and learn all we want to know about the situation. So let's start. First derivative test. F dt, because it's too long to write it. And the first derivative test will give us the regions of increase and decrease. So let's go with, I guess, this gives regions of increase slash decrease. It also gives min max. We're going to discuss that one as well. So how does this work? Well, you find your critical points and you partition the domain using those critical points. Now remember, critical points would be min, max, inflection, and vertical asymptotes. And then you would be able to look at the first derivative and see if the derivative is positive or negative. What we learned long time ago is that if the derivative is negative, function is decreasing because it would have a negative slope on the tangent line. And if the first derivative is positive, then it has a positive slope, which means function is increasing. So let's take a look at this situation. So what we are going to have, let's say, is a function y equal, or f of x, better, equals x squared. I know, scary function, right? Now, and for this function, we differentiate, we get 2x, set that equal to 0, and come up with x equals 0, compute the y value, and find the 0, 0 critical point. All of this was done last time, y to 4.1. Now we know x squared, we know this is a minimum, but we can use the first derivative test to show that this is a minimum while figuring out the regions of increase and decrease. So now, how does this work? Well, you take a number line, in our case, domain negative infinity to positive infinity, and you partition that one at your critical point. In this case, we only have one critical point, which is 0. That's the critical point. Then you pick a test point in each region. So you pick the test points. And now, the first derivative test, f prime of -1. Well, that's 2 times -1, right? Your f prime function is 2x. If your x is replaced by -1, you will get -2, which is smaller than 0, which implies that the function f of x is decreasing on that region. Actually, I have to move these test points. That's a bad spot because I need to draw a decrease arrow up there. So I can put here. There we go. Now we test the other test point. That's 2 times 1. That gives you +2. And that means that f of x is increasing. Oops. Which would give us arrow up over here. So we have discovered what the first derivative test is all about. And look what you get for free. Do you see the shape? So clearly your critical point at 0 is a minimum because the shape that you draw shows that it's a minimum. You could have had the shape like this. Then it would be a maximum, right? If this arrow went up and the other arrow went down, then they connect and make a maximum on the top where the 0 is. So it all depends on what you get here and whether you draw the decreasing arrow or the increasing arrow. This is a decrease and that's the increase. We always write from left to right, the way we read. So the arrow going down as you move to the right is a decreasing arrow because the value is going down as you progress forward in time. And the other arrow goes up, which means increase in value as time goes forward. So now we are ready to, with this example, right? We were able to determine that this critical point is a minimum. And you get that for free when you do first derivative test. So first derivative test will tell you the intervals on which the function is increasing and decreasing. And then also it will give you what the critical points are, whether they're min or a max. Now, I'm regretting that I put this in red. I'm just going to change the color of this real quick because it's going to clash with my definition / theorem, whatever, for first derivative test, because that's going to be red and boxed and all of that stuff. This was just a calculation. So let's write down first derivative test. Here we go. If f computed at the test point C, sorry, f prime computed at the test point C is less than 0, then f of x is the increasing around x equals C. So your x equals C, C is the test point. Second part, if the derivative, no, sorry, less than 0 is decreasing. If f prime of C is larger than 0, then f of x is increasing around x equals C. Again, we learned this all the way back in 3.2. We never gave it a name, right? We never defined it this way, but we did learn it, and now we're just going to put that in a box. Now I am going to go back into 3.2 and look for it. There you go. When f of x is increasing, the derivative is positive. When f of x is decreasing, the derivative is negative. Now, we are starting with derivatives and make conclusion, right, on what the function is doing. So now we say when the derivative is positive, function is increasing. So we just read this the other way for our new section. All right, let's go back. So now you can use the first derivative test to test any function you want. Let's work on another familiar function, f of x equals 1 over x. That's a familiar function. You know what the graph looks like. You know that the entire graph is decreasing all the time, but now we're going to prove that. You know that there is no min and max on that graph. You know a lot of stuff about that graph, and now we're just going to show all of those through calculations and the first derivative test. So now, if we just draw a little bit here on the side, right, we see that there is a decreasing piece, there is a decreasing piece, and there is no min slash max. And we should be able to compute all of this without we should compute all of this without looking at the graph, because now we are pretending that we don't know what the graph looks like. So here we go. The first order of business, get the derivative, and that's going to be negative 1 over x squared. So now when you set that equal to 0, you cross multiply, you get negative 1 equal to 0, which is nonsense, right? That means no critical point. However, f prime of x does not exist at x equals 0 because vertical asymptote at x equals 0. Aha! So there is a critical point, but the critical point will not be min or a max, right? We don't have the y values and so on. The critical point is the vertical asymptote, and we are going to partition right there. Now, what is my domain? Domain for this one is negative infinity to 0, union 0 to infinity, because there is a vertical asymptote at 0. Domain of all real numbers is interrupted at that one point. So what do? I draw my partition, which is again negative infinity to positive infinity, and I put my, in this case, vertical asymptote partition right there. And then do what? Pick test points and compute. Right? All the same as before. You can pick literally any number, right? You can pick 3 over 17 if you want. It's fine. You can pick any number in that region as a test point. And then work your first derivative test. So first derivative of negative 1 is going to be negative 1 divided by negative 1 squared. Right? This is your first derivative right here. And you are going to plug in negative 1 for x, your test point, and you are going to get negative 1, which is less than 0, which means that the function is decreasing, right? You got that, and by the thing we said earlier, function is decreasing. Now, f prime at 1 is negative 1 over 1 squared, which is also negative 1, which is also less than 0. Oops. And that one is decreasing as well. So function is always decreasing. And you can see that there is no min and max because your minimum has to be decrease followed by increase. Your maximum has to be increase followed by decrease. And what we have is decrease and then decrease again. So there is no min and max in that configuration, as well as there is no min and max when you have increase, increase. There is no min and max there. They have to alternate in order for min or a max to appear. So by understanding that, we confirmed that there is no min and max for this function. We confirmed that the function is always decreasing. We confirmed that there is a vertical asymptote at 0 because the function was not differentiable at 0. So we literally confirmed everything we knew from a pre-calculus course, everything we knew about 1 over x. You learned that in that section 2.6 on rational functions. That's when you learn specifics of 1 over x function. All of those things that you have learned there about this 1 over x rational function, we now confirmed using calculus first derivative test. So no min and max, always decreasing vertical asymptote at x equals 0. And now, what do you put for the answer? And I just remembered that I didn't do this for the previous problem, which is terrible. Your answer is, you will say 1 over x is decreasing on entire domain. That's it. This is your answer. Because the question is, find the intervals of increase and decrease. And we found that the function is always decreasing. Now, if you do look at the graph, right, I'm going to erase it, but you can see that if you are walking right here, you would be going down. If you're walking right here, you would always be going down. So it is, as you move to the right along this 1 over x function, you are always going down. So that's that part. Now let me go back and fix my terrible terrible thing over here. Yeah, I have to do this. I have to do this because I have to squeeze the answer over here. I forgot about that. So f of x is increasing on 0 to infinity. F of x is decreasing on negative infinity to 0. And that you get from this partition graph, right? You can see negative infinity to 0. That's the interval, and you have a decrease. So decrease on negative infinity to 0, and then on the other side, 0 to infinity. That's this part. Function is increasing. So you read that from this diagram. You don't need to have a graph. We do not draw any graphs here. We just look at the diagram and say, okay, here is the region for increase, here is the region for decrease, and you move along. Cool. And I would like to work out an example from homework. So these were the two functions that we are familiar with, right? Call them vanilla functions, whatever. Friendly functions. When you look at your increasing and decreasing functions problems, 19 through 44 in textbook, you are going to find a whole bunch of trig, higher polynomials. You're going to find a whole bunch of square roots, and you're going to find ln as well, inverse tangent, and all of these things. So I guess let's do 2. I was planning on doing 1, but let's do 2. We can do one of the trig and maybe a square root or something. What should be good? Should we do... Yeah, why not? It looks bad enough. 32. It says the function f of x is given as square root of 2 sine x minus x on the interval 0 to 2 pi. So they chopped up the interval, so we don't have to probably deal with a lot of these increase decrease forever situations. And we already have our domain, so I don't have to look at the domain of the function. Domain is restricted. So I can immediately jump into derivative. Copy the constant. Then we have derivative of sine is cosine, and then minus 1. There are no asymptotes and weird things happening here, so we don't have to worry. We don't have to worry about the root x. Sorry, about this function being not differentiable and having that situation, right? There is a point for. There is a critical point when the function is not differentiable, right? So we just have this and we equal it to 0. And that will give us this equation to solve. Now that equation works out to be cosine x equals 1 over root 2. Because right, you move 1 to the right and you divide both sides by root 2. Now you rationalize this because we don't like root 2 in denominator. And you come up with a cosine x equals root 2 over 2. Now that's a standard value that you learned, and the cosine is root 2 over 2 at pi over 4, the 45-degree angle. But it's also root 2 over 2 at 3 pi over 4. So if you draw your cosine graph, going from 1 all the way down to negative 1, and then you draw the root 2 over 2, it intersects twice at pi over 4. And so how much is that? This is pi over 2, this is pi, this is 2 pi, so 2 pi, so 7 pi over 4. I was wrong. Okay, so cosine is x is equal to pi over 4 and 7 pi over 4. These are my crit points. Those are critical points. And we got that by solving this basic trig equation. So now, since there are no vertical asymptotes and no other points to partition, I take my 0 to 2 pi and I partition at pi over 4 and 7 pi over 4. So these are my values. So now I want to find test points and go from there. The easy one is a test point pi. Actually, I should extend these up because we need to create those bins where the lines, the arrows are going to go in, right? So that's the easy one, pi, because it lies halfway between 0 and pi over 2, so it's definitely in there. So we don't have to worry about that one. What we do need to worry about are the other two test points, and this one over here, we can put pi over 6. That's a good value. Pi over 4 is 45 degrees. Pi over 6 is 30 degrees, so that's smaller. So 30 is definitely between 0 and 45. And pi over 6 is a nice value for us to compute. And we'll do the same on the other side, except on the other side you have to go to pi minus pi over 6 to find what that value is, because you are taking away pi over 6, guaranteed to be inside that interval. And that's 11 pi over 6, right? Because when you do the common denominator, it will be 12 pi over 6, so 12 minus 1 is 11. Okay, cool. So now we have the test points, and all we need to do is to run our first derivative test using these test points. So now we have three calculations. So we have f prime at pi over 6. Now remember, you have to go find your first derivative, and that's where you plug in pi over 6 test point. So that's root 2 cosine of pi over 6, everything minus 1. What is this equal to? Well, it's root 2 cosine of pi over 6. Now, if you study the chart that I talked about earlier, you know that the cosine of pi over 6 is going to be root 3 over 2, and then you have minus 1. So now, this becomes root 6 over 2 minus 1. And you don't need the answer here down to like 50th decimal. You just need to know if this value is positive or negative. That's all you need. Because if it's positive, you draw the arrow up. If it's negative, you draw the arrow down. That's all it is. So now, is this positive or negative? And obviously is positive without computing, because root 4 over 2 minus 1 would be 0, right? Root 4 is 2, 2 divided by 2 is 1, 1 minus 1 is 0. So if this was a 4, then it's equal to 0, because it's more than 4, the whole thing is more than 0. So we have increase over here because it's larger than 0. Now we do our easy calculation, f prime of pi, which would be root 2 cosine pi minus 1. All right, so now root 2 cosine pi, that's root 2 times, and cosine of pi is negative 1. You can see that on a graph all the way on top, right? There is a cosine of pi is negative 1. It's the lowest point. And then we still have minus 1. So this is negative root 2 minus 1. Well, that's going to be negative because you have a negative number minus 1. Well, that just makes it more negative. So we have a decrease over here. And finally, we have f prime of 11 pi over 6, which would be square root of 2 cosine of 11 pi over 6 minus 1. And that one is going to give us exactly the same value as the top, because you can see that the value is still root 2 over 2. It's on the same elevation for the cosine. It's on the same elevation here for 11 pi over 6. So it's going to give us the same calculation as the top, and we have increase. Now, please, guys, make sure that you know that these don't always alternate, right? We had that 1 over x where we had this situation. So they're not going to alternate all the time. Some problems you get them to alternate. Some problems you might have down, down, up, right? It doesn't matter. You will get configuration through calculation. You will know what it is. You can't just compute the first one and just say, okay, I'll alternate from here, and you know. So the problem governs what you get. And alternation is sometimes there, sometimes it's not. So there we go. So what have we got for free? We got for free that there is a max at pi over 4, and then there is a min at 7 pi over 4, which were our critical points. You have to now go back and compute the y values for it. But it is given, right, that you have a max because you are getting that max shape over here, and then the other one clearly gives us the minimum shape, right, which is that one. So that was a trig example, and now we get to write our answer. Remember, the question is asking you to find intervals where the function is increasing and decreasing. So what do I have? F of x is increasing on 0 to pi over 4 union 7 pi over 4 to 2 pi. These are the two places where the arrow goes up. Therefore, function is increasing. And given function f of x is decreasing on pi over 4 and 7 pi over 4, which are in between the maximum and the minimum, function is decreasing. So that all makes sense. You can also add to this that there is a minimum, right, at 7 pi over 4 comma, you compute the y, and then the maximum at pi over 4 comma whatever the hell the y is. You have to, well, let's compute it, whatever. It's not the end of the world. We have our function. So for maximum, it's function computed at pi over 4, and that was root 2 times sine pi over 4 minus pi over 4. Remember, it was minus x. Original function was minus x. So you're subtracting pi over 4. And this is not going to be a whole number, not even, right, with a pi. Because what you are getting now, sine of pi over 4 is root 2 over 2. So you're getting root 2 times root 2 over 2 minus pi over 4 is 1 minus pi over 4. That is that's a positive number because, right, pi is 3.14. So this number is going to be less than 1, and then 1 minus the number less than 1 is a positive number. But this is your y value. So for max, we have 1 minus pi over 4. And you compute the same way the y value for the minimum. You plug in 11 pi over 6, that's going to give you a negative, so it's going to be what? It's going to be negative 1, right? Minus, I think, minus pi over 4. So 11 pi over 6, because the sign does this. 11 pi over 6 would give us a negative. Not 11 pi over 6, 7 pi over 4. 7 pi over 4 would give us a negative value. So you would have negative 1 minus pi over 4. Yeah. For y. And that's it. That's the way you compute the values for the y values for your min and max. And as I said, you get this for free. Because as soon as you figure out what the increase and decrease are, then the min and max have to follow and plug in there. All right, let's take a look at one more problem. And then we are going to switch to the second derivative test for concavity. It's a little bit longer section. We have these square root problems. We had the ln problems. we have the inverse tangent problem. What do you want to see? I can't do every single problem. I mean, do you want ln? Do you want e? Do you want inverse tangent? Do you want the square root? Someone pick quickly. Which one?
Inverse tangent.
Inverse tangent, problem 44. Your function f of x is given as inverse tangent of x over x squared plus 2. And that's all it's given to us. So the denominator can never be 0. And because the denominator can never be 0, we have the domain here to be all real numbers. Inverse tangent graph, when it's vanilla graph, right, the original inverse tangent, graphs this way. So it has the domain forever. And that can be ruined if the argument becomes undefined at any of the points. But x squared plus 2 is always positive number, can never be 0. Therefore, we don't have any issues in a domain. So the domain here would be negative infinity to infinity. Now that's important because of the partitioning, right? We have to know domain. Now we have to take the derivative of this mess. I am going to write on the side the inverse tangent as the most important, maybe even the only important derivative of all inverse trig function derivatives. Inverse tangent is given as the derivative of inverse tangent of any function, and in this case we have this mess, is going to be f prime divided by 1 plus f squared. So that's your function that you are dealing with. So now the derivative is going to be a little bit tricky, but such is life. We're going to have 1 plus and then function squared. And then we need the derivative of this on top, and that's a quotient rule. So we have x squared plus 2 squared, x squared plus 2 times the derivative of top, which is 1, minus copy the top, which is x, and then derivative of the bottom is 2x. So I just need to grind through this algebra to fix it. So we have the simplified form. This derivative is really a mess. I am going to expand the top and have the x to the, oops, it's a double fraction everywhere, x to the 4th plus 4x squared plus 4 minus 2x squared. Now we have the bottom here, stay x squared plus 2 squared. And then 1 plus, I'm going to split this way because now it's much easier and nicer to simplify, because you see that you can hit both of these by x squared plus 2 squared, and that will kill the double fraction, which simplifies everything a lot. You want to simplify these things. You don't want to compute in this mess. So hello algebra, right? On the top, this just cancels, so you get your x to the 4th plus 2x squared plus 4, right, when you combine like terms. Denominator canceled. On the bottom, you have the x squared plus 2 when you multiply into 1, and then just plus x squared on the second term, it cancels. And finally, our first derivative is x to the 4th plus 2x squared plus 4 divided by 2x squared plus 2. That's the derivative. And now you set this equal to 0 to find those critical points. All right, so now we have the problem when you cross multiply, all you get is x to the 4th plus 2x squared plus 4 equal to 0. And you need to solve this. Now, the issue with this is that you have to factor this, and it's the 4th degree polynomial, and those are nasty. Polynomials are very nasty to find zeros. They're cool when they're quadratic, because you can use quadratic formula to find zeros. For a cubic, there is also formula. It's long, but you can do it. Like the 4th degree, forget about it. And for 5th degree and up, doesn't even exist. There is a proof that says that it cannot be, the formula cannot be obtained at all. So polynomials are nasty, and that's why we have all of those hoops that we jump through, right? The rational zeros and all of that stuff you learn in pre-calculus. Just because, the polynomials tend to be the nastiest functions for us to find zeros and to factor. Everything else works nicely. So over here we can jump into the substitution method, right? We can say u equals x squared, which would tell us that u squared is x to the 4th, and that would reduce the problem into a basic quadratic problem, where you can use the quadratic formula. So that's negative b plus minus b squared minus 4ac divided by 2a, and you quickly realize that you have 4 minus 16, which is negative 12, over 2, and the solutions are complex. So if those solutions are complex, then x is also complex. So x solutions are not real numbers, therefore no critical points. We have also no asymptote, and what this means for this problem is that the entire function is everywhere increasing or everywhere decreasing, right? And you can compute that. So if you go and say, all right, now let me figure out my oops, these endpoints are not good because this is negative infinity, positive infinity, right? And you go ahead and you pick a test point. So I'll write this in blood. All one partition. The whole thing is just one partition. And the reason why is only one partition is because there is nothing to partition. There are no vertical asymptotes, no critical points, literally nothing, right? It's just one piece. And you can pick any point, any number that you want to think of, that you can think of, from negative infinity to positive infinity as your test point, and test just that one number, because the whole line is a single partition. And obviously we're going to pick 0 because lazy, right? Now go and find your derivative, which is this, and then compute your f prime of 0. Now all of the x to the 4th is 0, everything is 0, you just get 4 over 2, which is 2, which is larger than 0, and the entire function is increasing. So the answer over here is f of x is increasing on the entire domain, negative infinity to positive infinity, and we have no min or max in the whole problem because there are no critical points to be min and max. So this problem just had really nasty algebra here through this derivative to deal with. But other than that, this was much shorter and faster problem than previous ones because everything was just one partition and the whole thing was just I would say fairly quick. It is messy, but again, like welcome to Calc 1, right? There's a reason why you guys make it a 4%, right? So that's the first derivative test, and now we're going to jump into second derivative test. Second derivative test, SDT. Now, second derivative test, guys, is going to have absolutely same steps, except done on the second derivative. You will be figuring out the second derivative. You will be equaling it to 0 to find inflection points. You will be using partitioning and test points. It looks exactly the copy of the first derivative test, except you're using second derivative, and the concepts that you are getting out of that are concept of concavity. Now, to understand concavity and why we need and why we bother with concavity, I like to, so let's start learning about concavity first, and then we'll do the second derivative test. So concavity. Now, I did already tell you, right, that something like this is concave up, and something like this is concave down. So if it holds the water, it's concave up. If it spills the water, it's concave down. Now, you can also have just parts of this, right? You don't have to have the whole U shape. You can just have this much, or you can just have that much. And in this case, you can have this much and that much, right? So any of these shapes. It doesn't have to be a full horseshoe or U, whatever you want to call them. Now, why do we bother? And to show why we bother with concavity, I like to make you think about money investment. So I'm going to give you 3 portfolios, and these 3 portfolios in time are accumulating money. They all start at the same value, say $10,000 investment, and they will all have different shape. So I'm going to have a shape like this, going to have a shape like this, going to have a shape like this. Someone please tell me which ones over here are making money over time. Come on, guys, it's not a trick question.
1 and 2.
Which ones are making money?
1 and 2.
1 and 2, definitely.
First and second.
Is third one making money?
Slows down over time.
It slows down, but is it making money? If you, okay, there is the YouTube chat kicking in. All 3 are making money. Yes, all 3 are making money. first, second, and third one are making money because when you wait a little bit in time and you see that they all have more money in the account after some time. So if I am to draw, let's say, a line like this, you can see that, right? And when you draw these initial investment lines, you see that the intersection point is higher. So all of these made money. Great. But which one is the best to invest in? Which portfolio? We have portfolio 1, 2, and 3. Which one would be the best to invest money in for the long-term investment?
First one.
2 because it's consistent.
Which one?
I say 2 because it's consistent.
Say 2 because it's consistent. And I believe someone said something else before you.
I said 1.
Why?
Because it's exponential.
It looks exponential.
Yeah,
So yes, the second one is the linear, and it's always earns money at the same rate. The first one is exponential growth. So the longer you wait, the money exponentially grows and you are gaining much more. And the worst one is obviously the third one. So if I am to color code this, I would say yay, I would say nay, and I would say hell no, right? If I am to do that. So and that's just considering the speed at which they are accumulating money. So this is exactly concavity, right? This is definitely concavity versus increase. You can see that all three are increasing. Now this one is concave up, meaning this second derivative is positive. This one is flat, and this one is concave down, meaning the second derivative is negative. Now this is second derivative is equal to 0. There is no change for something like this, but this is already a rate at which you are making money, so it's a little bit confusing if you compare this to the first derivative as well. But the idea of having a concave up graph is that the concave up graph will be accumulating stuff faster than the concave down graph. So the one at the bottom, the third one, is still making money, but the longer you wait, it's going to be slower and slower and slower and slower. And I like the comment that is on YouTube saying that it depends on how long you are investing for. And that is the perfect. For the long-term investment, you definitely want number one, right? And for the short term, right, would be this one because it has this burst, right? And then it kind of slows down. And, in time, where the other one looked like this, right, you can compare now 1 versus 3 on the same graph. You see how 1, which is concave up, is going to shoot up, and the concave 3 is going to sluggishly accumulate money. But yeah, it does also depend on the term. However, we never invest money for 3 days or 3 months. Investments are done a year or 20 years, and you definitely starting, if you start saving now, right, at this point in life, it accumulates to a lot by the time you're 70, because imagine 50 years of investment, right? The money is made through investments. You can't you can't be excessively rich if you don't own a company or invest money or something like that. So that's where the big game is played, right? Going to school and getting engineering degree guarantees the middle class, right? So you are making a trade-off to some extent from being excessively rich to having some security, because to get excessively rich, that means take a lot of risks, right? Take a lot of risks. and be extra smart to manage all of that so you don't lose it, because it's very easy to lose it, which is why, right, only certain people are able ever to achieve that state. Not everyone is excessively rich. It really takes a lot of brain and determination to do it. Okay, so now let's take a look at the second derivative test. So second derivative test says if the second derivative, and you have your test point C, is bigger than 0, then f of x is concave up around x equals c. And the second part, right, so again, part 1, part 2, if the second derivative of c is less than 0, then f of x is concave down around x equals c. Now, we are going to add the third one because we did not talk about it. If f double prime of c is equal to 0, then there is inflection point at x equals c. Now, what is inflection point? Inflection point is the point at which concavity changes. So we are going to find the second derivative, set it equal to 0, find the point at which concavity changes, and we are going to do partition. So now, let's go, I guess, blue. We partition on inflection points and vertical asymptotes. So the same, your first derivative test partitioned on critical points, which included vertical asymptotes. Now you have inflection points and vertical asymptotes. So the initial problem, the easiest problem we can practice, is going to be x cubed. Right, that's the first one. And to find the inflection points and so on, we find the first derivative, which is 3x squared. And then we find the second derivative, which is 6x. And that's equal to 0. So now, what we do is we take a look at the equation over here. And we get that x is equal to 0, which gives us our inflection point. So when we have this inflection point, that is where we partition. So I have partition at 0, and we know that the domain of x cubed, like every other polynomial, is all the way from negative infinity to positive infinity. So now that I have this, I am going to choose the two test points. Those are those C's. Now, obviously, we choose easy, cheap stuff, -1 and 1, and we do our second derivative test. Second derivative computed at -1 is going to be 6 times -1, because we have to use second derivative to compute. And that's going to be -6, which is less than 0. So concave down, CD, concave down. You can also put, if you want to, the shape. And then the second derivative computed at 1, which is 6 times 1, is equal to 6, which is larger than 0, and that's going to be concave up. So concave up over here. Now, the 0, 0, 0 is inflection point. Right? When you find your y value by placing your inflection 0 in here, right, you will get the y value, and that's going to be 0, 0. So now let's take a look at the x cubed graph and make sure that all of this fits, which it does, but let's see it. So this is the x cubed graph, and what we see here is the 0, 0 inflection point, and you can see on this side concave down. Because if you are to, continue this motion this way, you would see the whole shape like the concave down. But we said that you can have only half of it. It doesn't have to be, the full thing. And now let's use, I guess, yellow or orange. This part over here, well, that part is concave up, because you can, right, have this shape and that holds the water, right? So we see that these parts, right, the concave down and concave up, and they switch, right, at our 0, 0 inflection point, IP. And that's that. So now, what is my answer? Because the question was, find the intervals, right, for concavity. We'll say f of x is concave up, let's say, on 0 to infinity, and f of x is concave down on negative infinity to 0. And those are that's the answer, because the question is, right, before the question was find the intervals of increase and decrease. Now find the intervals of concave up and concave down, right, where the function is concave up and where the function is concave down. The next example clearly should be a trig example, because for the trig function we have a wave, let's say for sine, and this sine has infinitely many min and max values, and infinitely many increase parts, infinitely many decrease parts, infinitely many concave up parts, concave down parts. So trig functions are absolutely amazing, sine and cosine, absolutely amazing for us to put all of this together into one packet. So find all for f of x equals sine x on negative infinity to positive infinity. I'm not even restricting the domain from 0 to 2 pi. I just want to have the whole thing to see all of the infinite values that we get. So now we have to do first derivative test to get all the increase and decrease, find the second derivative test, do the second derivative test to find all of the concavities. The increase decrease will also give us min and max. So we'll have everything as we go through this. So we start with, we already know domain is all real numbers. We know there are no vertical asymptotes or anything like that. So we can just plow through calculations in order. F prime of x is equal to derivative of sine is cosine. And as usual, right, I like to highlight that so I can quickly find it. I need to set this equal to 0 and solve the equation cosine x equals 0. Now, for me, the fastest way to solve any trig equation is to draw a graph, because I see it goes through pi over 2 and 3 pi over 2. Right, that's a pi and that's a 2 pi at the end. So I know that the cosine is going to have zeros at x equals pi over 2 plus 2n pi and 3 pi over 2 plus minus 2n pi. Those of you who missed some of this trig before, right, this will continue forever, and the next time when it hits over here, the same 0 will be 2 pi apart, and then when it hits the same 0 will again be 2 pi apart, because it is the period is 2 pi. And then how far out do you want to go and look for your next 0 is this n counter. So you say that this is n times 2 pi, which is how many bumps you want to go at 2 pi intervals. So to jump to the next is 2 pi, and that would be, so for this one, for this root over here, n is 0. For this root over here, n is 1. For this root over here, n is 2. And then it goes like that. So when I write these solutions like this, we have to write that n is equal to 0, 1, 2, 3, on and on. Okay, I can leave. This is n equals 0. This is n equals 1. This is n equals 2. Going on forever. Now, if you pick minus signs, then you are going this way, and you have your n, right, to be, right, if this is a negative, right, you're subtracting 2 pi, so you're going to the left. So this gives you the infinitely many critical points. And now we need to partition, right? So when I draw my infinite domain, I can partition at all of these values. So here is partition here at, let's say, pi over 2. Here is the next partition at 3 pi over 2. Here is the next partition, right? When you 3 pi, so that would be plus 2 pi, which is 5 pi over 2, right? It goes like that. And over here you are subtracting 2 pi, so write pi over 2 minus 2 pi. That's going to be 4 pi over 2, so that's negative 3 pi over 2, negative oh, I skipped one. Negative pi over 2, there we go, negative 3 pi over 2, and so on. I see the question on YouTube saying, are we supposed to be working on a second derivative? We will. Right now I am working the first derivative test for increase and decrease, right? I said find all. I didn't say find just concavity. I said find all. All is increase, decrease, mean, max, concave up, concave down, right? So you have all of the inflection points. So this is a full problem that is asking you something similar like on the exam. It will say, I mean, on exam I usually split the two, right? Do the first derivative, do the second derivative test. But when you need to graph a function by hand, you have to do both of these. So technically this is a good prep for the next section. All right, so we have all of these. Now, test points. Well, 0, easy. Pi over 2, easy. Pi, easy. Negative pi over, why did I say pi over 2? Not pi over 2. This is pi. I'm losing it. This is pi in between these two, and this is a 2 pi in between these two. There we go. And then negative pi. So they will carry through. All right, so now f prime of negative pi is the cosine of negative pi. Cosine is even function, so that negative doesn't matter. And cosine of pi is -1, which is less than 0, which means a decrease over here in the box. Then f prime at 0 is cosine of 0. Cosine of 0 is 1, larger than 0. We have increase. Then f prime at positive pi, which is the next test point, is going to be cosine of pi, which is again -1, which is less than 0, which means decrease. And then just one more, even though we don't need it. F prime 2 pi is cosine of 2 pi. Cosine of 2 pi is 1, larger than 0, increase. Now we are expecting this to alternate because it's a cosine and sine functions. They just alternate like that. And what we found here is that at pi over 2, you have all of your max values. And at 3 pi over 2, you have all of your min values. So that was free. That was free from this calculation. So now, I just do the second derivative test. So first derivative test is done. I got min and max values. I got increase and decrease. We're going to write the answer at the end in one spot. I still need to do the second derivative test for this. So now, second derivative test. Second derivative is, our first derivative was cosine x. The derivative of cosine is negative sine. So that's going to be negative sine x. And we will be using that one to compute things. And now negative sine x equal to 0. Now that happens at n pi, every n pi, because your sine, this is a negative sine x, which means it's going to go down and up and down and up instead of up and down, up and down. Just because it's negative, right? That negative just flips the function. That's the basic pre-calc1 rule, right? That the negative flips the function on the x-axis. You can see that there is a 0, there is pi, there's 2 pi, there's 3 pi. So x equals n pi is where you are going to have all of your inflection points. Remember, when you set second derivative equal to 0, you get inflection points. So now that I have all the inflection points, I know where to partition. I can partition a couple of these from negative infinity to positive infinity. I can put a 0, negative pi, positive pi, and then just pick values in between to test. Here is pi over 2. Here is 3 pi over 2. Here is negative pi over 2. Here is negative 3 pi over 2. Right, whatever values you want to pick in between these. Now, there will be more partitions this way and more partitions this way because they go forever, which is why we have this n business over here. Actually, I just noticed that I didn't do too good of a job here. I was supposed to say plus minus n and define n as 0, 1, 2, 3, and then say inflection points. Because that plus minus n, right, the minus allows us to go this way, and that's that. Now, some people like to just put n pi and then go 0, plus minus 1, plus minus 2 for n. It doesn't matter which way. It's just faster to write it the way I wrote it, because you don't have to put million plus minus signs in n. All right, cool. So now, second derivative, computed at negative 3 pi over 2, let's say. There will be negative sine x, so negative sine of negative 3 pi over 2. Negative sign is odd function, so negative jumps out and kills the minus in front. So you just have sine of 3 pi over 2. Now regular sine of 3 pi over 2 is negative 1, which is less than 0, so that means concave down. Now, the second derivative of negative pi over 2 is going to be negative sine of negative pi over 2. Again, sine is the odd function, minus goes in front and cancels this one, and we get positive 1. That's larger than 0, so concave up. And then they will alternate, so I'm not wasting time over here computing all of these things. And we have our intervals of concave up and concave down. Now, there is one thing that I want to point out here, which is connection between the first and second derivative test. Observe that you have, let's say, from 0 to pi, you have a concave down piece, which means that at pi over 2, there should be a max. And that has to match your first derivative test. So that should be a common sense, right? This is where the 0 is. This is where the pi is. And you have a concave up piece between those. And midway between 0 and pi is pi over 2. And by looking at the concave down part, concave down is the upside down U shape, we better find pi over 2 a max. There it is. Pi over 2 is max when n is equal to 0, right? So there are these checkpoints along the way that if you really understand what is going on here, you can check your work and you can see inconsistencies, and if you did some calculation wrong before it's too late to check and fix these things. So finally, we have our answer. And our answer consists of increase, decrease, mean and max, and inflection points and concavity. So all of that stuff. So let's start with the cheap stuff. Max at, and now we have that pi over 2 plus minus 2n pi, comma 1, that's the y value, right? That's the max. Then we have the min at 3 pi over 2 plus minus 2n pi, comma negative 1. The mean values for sine function are all at negative 1. And again, 2n pi that n will define for all of our problems. Then we're going to take a look at the decrease. So decrease happens at all of these intervals. Now, decrease. Go and pick the basic decrease and make sure you put those n pi's in there. So we have pi over 2 plus minus 2n pi, comma 3 pi over 2 plus minus 2n pi. So that was the decrease between the two. And now increase, you can use this one or you can use that one. I don't care which one you use. For increase, pick any one of them. I'm going to pick this one because usually that's the one because it's symmetric. So increase at negative pi over 2 plus minus 2n pi, pi over 2 plus minus 2n pi for increase. Inflection points at n pi comma 0, because when you compute sine at any of the pi values, it's going to be 0. So sine of 2 pi is 0, sine of 3 pi is 0, sine of 100 pi is 0. All of them are 0. So those are inflection points. And then now we have concave up and concave down. So concave up regions are 0 to pi. So we're going to say 0 plus 2n pi, comma, pi plus 2n pi. That's a concave up, right? No, that was concave down. That was concave down, right? 0 to pi. So 0 to pi, and then increase every 2. So it's concave down. And the concave up is going to be pi plus 2n pi, comma, 2 pi plus 2n pi. That's the next one. Yes. Pi, and then the next partition here would be 2 pi, so yes. Okay, that works. Now you don't have to write this 0. You can just say 2n pi. And then we need the minus signs here as well. There we go. Perfect. And now for all of this, n is equal to 0, 1, 2, 3, dot, dot, dot. That's the answer. This gives everything for the sine function. You have your min and max values with their y values. You have your inflection points and pi with a 0. And you have, oops, I forgot to put plus and minus there. Terrible. There we go. Then you have your increase and decrease intervals, and you have your concave up and concave down intervals. And this is considered the full answer that provides everything that we have seen for the sine problem. And that was sine x. Now obviously, right, you can have functions that are composite functions whose derivatives are going to be a living nightmare, solving those equations. And I'm not talking only about the trig, I mean literally anything else. You've seen the algebra in that inverse tangent problem. Inverse tangent is a very friendly function in general, but you know, once you toss in that rational function in the inverse tangent, it created a lot of mess, right, that we had to go through. These problems are very right. You learn the difference between hard and annoying, right? These problems are not hard. These problems are annoying. They take a long time. They're very picky, easy to make a mistake. But the concept is, you know, take a derivative first or second, set it equal to 0, get the points, partition stuff, and pick values. It's arithmetic most of the time. The only calculus you do here is to take two derivatives. So from the calculus perspective, this is a joke. But when you look into the amount of algebra and amount of calculations that are piled up with this, plus memorizing obviously first and second derivative test rules and what it means, right? It all adds up into one beautiful big mess, as you can see over here. So first derivative test figures out increase, decrease, and min-max. Second derivative test figures out concave up, concave down, and inflection points. Both of those tests are done exactly the same, except they use a different derivative as input in calculation. So first derivative test, right, you will find critical points and then partition over critical points and vertical asymptotes. Second derivative test, you set it equal to 0, second derivative equal to 0, and then you partition again over inflection points and vertical asymptotes. In both cases, you pick your test points, you plug test points into the derivative, and then just figure out whether that derivative gives you smaller or larger value than 0, and then you make your conclusions on whether the function is, right, increase, decrease, concave up, concave down, whatever you're looking into. And that concludes this section, which also concludes this class. I'm going to disconnect and connect to my office hours. Those of you having questions, please join immediately right now. Join to my office hours because we ran out of time. I don't have time, unfortunately, to answer questions here. So please join. The Zoom link is posted in announcements in Canvas. So please join there, and I will see the rest of you on Monday. We are going to graph functions by hand, and then we're going to have a review for the exam coming up next weekend. Not this one, but next one. So see you all there.
Thank you.
You're welcome. Bye.